Hello everyone, and welcome to the second of 5 live webinars for Cisco CCNA V3, a short course presented by IT Masters on behalf of Charles Sturt University and the Information Technology Professionals Association, or ITPA. My name is Guy Coward, and I'll be your MC tonight and for the duration of this course, and your mentor is Matt Constable, who you'll hear from shortly. As always, before we begin, just some housekeeping, beginning with Zoom functions, which I briefly went through last week, but we'll go again. We really do hope you're enjoying the ability to chat with panelists and amongst yourselves during the webinars. As James said, you can choose one or both. And as per last week, we ask that you direct questions that are directly related to course material to the question and answer section, and ask administrative questions via the chat function as well as your chat. We have quite the team on board tonight. Holly, James and Diane will be going through some of the chat questions, and Robert will be around as well. Also, for those of you who haven't seen the course page, the materials are almost all up and the forums are going fantastically well. Matt was just telling me how there's been some great conversations going, so keep that up. Towards the end of Matt's webinar tonight, we'll hear from Jason Howarth from CSU. He will be relating this short course to what CSU are teaching in a similar vein. And of course, Robert Hudson, the president of ITPA, is around, but he'll likely just be his usual self on the chat. Anyway, could you please all welcome your mentor, Matt Constable. Thank you, Matt.
Thanks, Guy. Thanks for the intro as ever, and welcome everyone to our second session. So this evening we're going to be drilling down on some of the layer 2 concepts that you need to get your head around for the CCNA exam. The most important thing, the most important takeaway from this particular week is all around spanning tree. Okay, it's a big component of the CCNA exam, and the CCNA structure going all the way from the Cisco certification structure going all the way from CCNA all the way to CCIE. So it's really important that you get your head around the big picture concept of what it's about, and how to configure it, and how the little bits and pieces work together to work with spanning tree. Now, just before I get into the content, I just want to mention a couple of things that have come up during the last week. So first of all, there were some questions about the answers to the subnetting exercises. Those answers are now available. They've been put up in the last 10 to 15 minutes, are now available on the Moodle site. And also there was some discussion about the differences between CCNA and CCNA 2 and V3 exams. Inside the discussion forum, I've started a thread which links to this document here. So this document here will show you all of the changes that Cisco have made between the version 2 and version 3 exams. Now, this particular page talks about ICND 1 and 2, which, as we spoke about last week, that's the 2 exam option. The single exam option is just these 2 exams put together, so the same changes are completely relevant. You'll notice, hopefully, as you read through it, that some of the topics that are on these are listed here. We talk about in great depth, and we also add a little bit of stuff that has since been taken off. And the reason we do that, the reason I've got that in there, is to give you the whole picture rather than just throw you in with the current new topics. There's a little bit of extra knowledge that I think is worthwhile you having, and I'll add it in as we go along. So if you find in some weeks we are talking about things that don't appear on this outline, the reasoning behind that is to give you that little bit of extra knowledge and a little bit of extra background to help make that transition easier. And for those of you that are currently going through the process of perhaps certifying for CCNA, it's always good to do that anyway, to see the linkages between the knowledge required at level 2, version 2 to go to version 3. So that's why the reasoning behind that. So have a look at this particular resource when you get a chance, and if you've got any questions, further questions about the structure differences, by all means pop them up onto the forum, and I can answer those as they arise. The second thing I just wanted to quickly show you is this book here. And the reason I'm mentioning it this week is this, and you'll notice, you'll laugh, because it was published September 5, 1999, and you sort of think how much benefit am I going to get out of a text that old? You will get a lot of benefit out of it, particularly the chapter on spanning tree. There's a couple of chapters on spanning tree that this book's got on it, and it's probably the most in-depth, comprehensive, well-explained, best description of spanning tree I've ever seen on any resource I've ever come across. And years ago, when I was going through the CCIE process, this particular book was seen as a bit of a Bible in the switching area. So even though it's old now, and yes, some of the spanning tree technology has progressed to obviously rapid spanning tree, multiple spanning tree, those sorts of technologies are now around. That's not addressed in this book. But the basics of spanning tree are covered better in this than in any other resource you'll probably find. So if you look hard enough, you will find PDF versions of this floating around on the internet, and I would fully encourage you to find a copy of this text somewhere, because it's perfect an accompaniment, particularly with relation to spanning tree. Okay. The other thing I wanted to address just quickly too was Guy made some reference to it just at the start there about there's a lot of resources available. I've put up a lot of different content, and yes, while that's true, you also don't need to read through every single page of every single detail of every single resource. There's a lot of overlap in the resources, and that's deliberate. So you've got a variety of resources to look at that are saying similar things rather than having resources are saying totally different things. So they're all there to help you. How many you read is up to you. As Guy said at the start, what you get out of it is what you put into it. So if you find that you're looking at a resource and it's covering over some ground that you already know, then skip to the next one. Find out what works for you. So absorb what is useful, reject what is useless. Okay, so let's get into tonight's little bit of historical stuff, which we sort of covered last week in a little bit, but it's good to just have this little bit of a lead into the layer 2 stuff. We know that switches are the main choice today. Hubs and bridges, not so much. Bridges and switches, often interchangeable language, meaning the same thing, are slightly different, but nowadays, basically, we just talk about switches. Hubs, as we talked about last week, work at layer 1 of the OSI model, single broadcast collision domain, slow, regenerate signals, lots of potential for noise, all sorts of stuff. So their legacy, you won't see any reference to those on the CCNA version 3 exam. However, they're good just to know a little bit about for comparison purposes, so that you can understand where the technologies come from and where it's now got to, and the transition states as it moves through. So if we just quickly look at a hub bridge comparison, we can see that so bridge or switch in this particular case is in the middle here, and we've got hubs on the outside. We can see that we've got one collision domain and shared 10 megabits of, admittedly it's a little bit old, this diagram, but it's the principles that count. A shared 10 meg of bandwidth on this side of the bridge, and a shared 10 meg of bandwidth with a single collision domain on this side of the bridge. What this is really showing is that hubs have no role in separating collision domains. One hub, one collision domain. Bridges, on the other hand, have a role in splitting collision domains. So if that bridge was not there, you would then have one collision domain with 4 hosts in it, all sharing 10 meg. Instead, now you've got 2 collision domains, 2 hosts each sharing 10 meg. Now you might say, okay, well, that doesn't sound very much. That doesn't sound like that would be a problem. And with 2 hosts on the network, probably not. But then think of each of these little computers as representing 200 hosts or 300 hosts instead of just 2. And then you start to get the idea that as you scale these networks up, collision domains and the separations of them actually becomes a really important concept. If we look at a switch, so similar functions to a bridge, but much faster with many extra enhanced features and software capabilities, which we'll look at some of those as we talk through the discussion tonight. In this case with the switch, we have 4 hosts connected to it, and we have 4 separate collision domains. So therefore, there's not going to be, and particularly in full duplex mode where you're able to transmit in opposite directions at the same time, very little, basically nil possibility of collisions unless there's something like a duplex mismatch, which then of course improves the throughput and the overall performance of the transmission between end hosts and your network overall. So switching. So the main role of a network switch is clearly to forward or switch Ethernet frames. So remember last week we talked about the OSI model at layer 2, we call them frames. So that's what we're basically going to be talking about in tonight. Occasionally I might slip and say packet, so please excuse me if I do that. But in general at layer 2 we're talking about Ethernet frames in this particular case. The addressing logic, so the addressing scheme that exists at layer 2 uses MAC addresses, and that's what we see with that layer 2 in the OSI model. We have a MAC sublayer and we have a LLC, or a logical link control sublayer. LLC we'll worry about for another time. Tonight we're mainly going to look at MAC, which is media access control. So that's related to MAC addresses, as you see on your network cards, which hopefully you will all be familiar with, and if not, you will be after this week. 3 primary functions that switch has to provide. So they need to decide when to forward or filter frames. So when do we send a frame out of a port? When do we filter it? So filter it basically means we're dropping it. Okay, so we either send it out or we don't. So it needs to decide how do we do that, which packet, see, I nearly did it then, which frames we send out, which frames we don't. They learn MAC addresses by examining the source address of the frames that come through each port, and we'll talk about that a little more very shortly. And then lastly, to create a loop-free layer 2 topology, okay, using spanning tree, and that's a big ticket item for this evening. Now, some of you are out there and probably saying, hang on, I think switches have some other functions as well. And yes, they do. There's other little bits and pieces they can do. However, in focusing on CCNA v3, these are the ones that you need to worry about. So filter or forward. So switches build a MAC address table. So basically a table that contains all the different MAC addresses that it sees as the frames pass through its switching fabric, through its ports. And the way it does this is it looks at the source address of a frame as it comes into the switch. So it looks at where the frame has come from, not where it's going to, but where it's come from. Because you think if you turn a switch on for a start or you reboot a switch, it has no knowledge of any MAC address. There is no MAC address table. The only way it can determine exactly which MAC addresses come through which port is by looking at the source address. If it only looked at the destination address, it wouldn't know where to send anything. So as a frame comes in through the switch, it looks at the source address and it says, okay, that source address I know came through, say, port 2, and it builds an entry in its MAC address table which says that MAC address comes from port 2. So as frames come into the switch, it starts to build a picture of the network from a layer 2 perspective, which MAC addresses are on which port. And as it does that, it gets bigger and bigger and bigger and bigger, gets a better idea of what's sitting out there on the network. And then when return traffic comes from a frame, it can look at the destination address, the destination MAC address, compare that to its MAC address table, and from that determine where it has to go. Okay? And we'll have a look at that in table. I think there's a couple of graphics coming up which will explain a little bit better than the words. But so it builds a table by looking at the source addresses. It compares the destination address of any frame to that particular table, okay, which I've just said, in order to determine whether we're going to forward it or filter the packet. So, for example, if the destination MAC address already exists in the MAC address table, the frame will simply be forwarded out the listed port. Okay, so say for instance, MAC address 1 is on port 1, and a frame comes into the switch that says I want to go to MAC address 1. It will refer to that table, see that it's out port 1, and it will send that packet directly out port 1, but it won't send it out any other port. So it's what's called filtered or dropped on all those other ports. So it only goes out the one port. However, if the destination MAC address in the frame is not known, so it's not in its MAC address table, then it has no choice but to forward it out all ports because it doesn't know which port it's got to go out. So it just forwards it out all ports on the particular switch, and away it goes. And that then creates that flood of traffic, which can cause issues if you get to the limit of the MAC address table memory. So you reach the maximum size it can be, it will then start spewing out packets everywhere. But an example for a bit later on. There you go. If I'd waited a bit, we could have done this. So if we look at the example, so in this case, if we first of all, so a frame comes in port 1, fast Ethernet 01, and it's destined for this particular address. Okay, so the switch looks at its MAC address table, which is down here. So second step is it goes to the MAC address table, and it can see that that MAC address is tied to port 2. So it sends that packet or forwards that packet straight out port 2, but it doesn't send it anywhere else. It filters it on all other ports. So forward out port 2 filters it on port 3 and 4 because these MAC addresses are obviously different. So in order to filter or forward effectively, they've got to build that MAC address table, examine the source address of each frame as it passes through the switch, as I said, and then builds that pairing between the source address and the incoming switch port. So it's not an outgoing switch port, it's an incoming switch port because you're looking at the source address. So again, in the example here, Fred sends a frame into the switch. We can see here that we've got an empty address table. So Fred sends a frame into the switch. The switch learns that Fred's MAC address, or the source address of this frame, comes from port 1. And so it makes that entry into the MAC address table. So that's the first entry. At the same time, Barney here sends a frame in, and it sees that that address associated with Barney comes in from port 2, and so it builds that particular link in the MAC address table. And then after that, traffic can pass bidirectionally between these two hosts directly out those switch ports without ever having to go anywhere else. You can see that's a big improvement on what a hub does, where a frame will come into a hub and it's just sent out all ports. So instead of sending it out 3 additional ports, it only sends it out 1. So a big improvement on performance. So as switches build this MAC address table, they automatically start filtering or not sending frames on ports that don't correspond to the destination address of that frame. So in other words, that's what we've been saying. If it knows where the MAC address has to go, it knows where the frame has to go directly from its MAC address table, it will send it out directly to the destination port, won't send it anywhere else. If, however, we're talking about broadcast or unknown unicast frames, so that is unknown from a destination address perspective, then those frames will be flooded out every single port. So broadcast and unknown unicast are treated in exactly the same fashion. They just send out all ports, with the exception, of course, of the port on which they were received. So if you send a broadcast frame in through port 1 and you've got a 24 port switch, it will go out all the other ports but not back out port 1, because the switch is clever enough to know, well, it came from there, so the host and all the other hosts that are attached to that segment will have got that broadcast already. All right, so is there any, just stopping for a sec, is there any questions on that particular section before I get into spanning tree?
Just someone has asked if you could go over what a collision domain is again.
Okay, so a collision domain is a segment on a network where all hosts will see all traffic. And there's if you think of it, probably the best way you can give an example, I haven't got the diagram up, that was from last week, but the best example you can think of it is if you think about a bus architecture, so a single cable with 20 or 30 machines attached to that single cable, like we used to have in the old 10 base T, B and C days. That's a single collision domain because any of those hosts can transmit at any particular time. And therefore, if they're all transmitting onto the same single length of wire at the same time, there is a potential for packets to collide. So there's potential for collision. And so a single segment like that, where there are multiple stations that can transmit at the same time, is known as that collision domain. Now you may say, well, how is that related to a hub? Why is a hub a single collision domain? A hub is effectively just a single long cable. That's all it is. You think of it as a bus architecture. Whereas a switch is a star architecture. So each port is unique to the host or the segment of the network that's connected to it. And therefore, it hacks up that collision domain into many multiple bits and pieces. So hopefully that's made that a bit clearer for whoever that was that asked the question. Okay, other than that, are we right to...
Oh, no, of course, now that we've got to question time, we've got a few flooding in.
Okay.
Does the switch send out all ports first to establish the port if the table is empty from Corey?
Yes, that's correct. So if the table is completely empty, the first packet that comes in, obviously it will learn the source address of that packet and put that into the table, but because obviously the destination address is going to be different, then it will flood it out all ports, correct, until a reply comes from that particular destination.
Ericsson has asked whether there's any linkage with an ARP table at this point.
Sorry, what was that? With the IP table?
ARP.
Oh, ARP. Well, yes, ARP tables and MAC address tables are similar. An ARP table is basically just a collection of MAC addresses that are matched up with the corresponding IP address that belongs to that end host. So it's sort of the next layer up. It's a level abstracted from that. So the MAC address table is really just MAC addresses connected to ports, whereas the ARP table is MAC addresses connected to specific IP addresses, regardless of which port they're hanging on. So they're sort of related in that they've got that common link with the MAC address. And as we see later on in a couple of weeks' time, we'll probably talk a little bit more around the communication path from layer 2, layer 3, all the way up to application layer. But they are separate entities, but certainly related.
Okay, and maybe just one more
Yep.
from Rob. Is it possible to have a duplicate MAC address? And if so, what problems would this cause on the network?
Yes, it is possible to have a duplicate MAC address. It shouldn't be, but it is. Generally, a MAC address, for those of you who aren't familiar with it, a MAC address has 6 parts to it, grouped in hex digits, so 2 lots of hex digits in each part. The first 3 lots of those hex digits, so the first 6 hex digits, are allocated to the vendor of the network interface card, whoever that may be. And the last 6 are randomly generated to be unique. So the idea is that every MAC address on every network should be unique, but that's not the case. There are certainly times when that can clash, and with modern operating systems, you can even change them anyway. So if there is segments where you have the same MAC address, then that will disrupt communication involving those particular hosts, because if you have 2 or 3 or 4, however many hosts with the same MAC address, they will all be purporting to own that MAC address when traffic starts flowing around. So there will be communication issues for sure.
Great.
There's a trick with routers that allows, but that's a discussion for next week.
Okay, plenty of questions still to go, but we might just keep pushing on. Hopefully we'll get to as many as we can. And yeah, feel free to post in forums if they're not answered, and don't by any stretch think it's a poor question.
All right, I'll push on. Okay, so loop prevention. This is where we start to talk about, as I said before, the big ticket item for this week, so spanning tree. So spanning tree is really the main mechanism, other than common sense cabling and design, to prevent loops in your network. Networks need to have redundant links. These are obviously good and very, very common nowadays in a number of different ways. However, if we have redundant links, then it is possible that loops can occur. Loops are generally a very bad thing in the network because they'll continue to circulate packets round and round forever and a day, and it chews up bandwidth and chews up processing power and chews up memory, and you get all sorts of nasty things happening, particularly when we're talking about broadcast or unicast frames. Broadcast and, unknown unicast frames. So broadcast packets, because they have no particular destination, they go everywhere. You can imagine if you had a loop in your network, broadcast packets could potentially go round and round and round and round forever. And I've certainly seen that in the real world, and it's a massive impact on the performance of your network. It gets to such a stage that you simply can't use it. And the only way to fix it when it gets to that stage is to basically power off the switch and start from fresh again when it's completely empty, and do some reconfiguration if possible, or make sure that you haven't got physical loops in your network. And this is where it's important to understand the difference between a hub and a switch. And in the old days, when we're using lots of stacked hubs, if you had that redundancy, you couldn't really have redundancy, because if you put in cables that went backwards and forwards, then hubs being stupid devices that just forward packets, things would endlessly loop around aimlessly forever, and you'd end up with very severe congestion on your network. So switches are a great device from that point of view, because they separate those collision domains, and routers help again by separating into broadcast domains. But certainly we need that with the capability to require physical loops is obviously much more now than what it has been in the past. And so the loop prevention stops things from aimlessly wandering, as I said. So if we look at this example here, this is just a quick example of what a loop can look like. We've got some redundancy in terms of the paths available between all these hosts. So if, for instance, this link went down, then we could still communicate via this way for Larry and this way for Archie talking to Bob. Or similarly, if any one link is down, there is still an alternate path to get to Bob from the other two devices. So that's generally a good thing. We want to have alternate paths. What we don't want is this looping around of endless packets. In terms of internal switch processing, there are three basic types. Now, one of these in particular, store and forward, and cut, some of these are quite old, but it's good to know the underlying theory. So this is one of those examples where these may not necessarily be listed on the CCNA exam topics, but they're useful from a knowledge perspective to understand how these devices have worked in the past and where they're going to now. So three main basic types that you need to understand for CCNA level. So we have store and forward. Now in this case, a switch will receive all the bits of a frame, okay, so it stores a whole lot in a buffer before it decides to forward the frame. Okay, so what this allows a switch to do is, if we remember from last week, layer 2 has a trailer, a frame check sequence on the end of the frame. So by the switch allowing the whole frame to come in, it allows it to check that frame check sequence to ensure that the frame is in good shape before it starts sending it out. Okay, but it's slow, because you think you've got a big Ethernet packet, so around about 1500 bytes for a maximum size Ethernet packet. 1500 bytes has got to come into your switch, does the frame checks it's okay, then it sends it out. So it's slow, you need lots of buffer space, very slow in relative terms. I mean, most of us are not going to see the difference in everyday life, but certainly slow from a switch perspective. We then have cut-through switching, where this is where the switch basically forwards the frame as soon as it can, absolutely as soon as it can. And that delineation point is the destination address at layer 2. Okay, because switch, remember, we work at layer 2. So as soon as it sees the destination address, it starts to forward the frame out whatever port it needs to go to. So straight away, so you can see much quicker than store and forward. However, if a collision or an issue has occurred later on in the packet, later on the frame, it's not going to pick that up until too late, until it's already started to transmit it. So if you've got situations where you've got, yes, you might have a switch, but you might have, say, 10 devices hanging off each port connected via a hub, for example, then there's still a potential for collisions to occur. In a cut-through environment, it can't detect those collisions. Okay, way it goes. So therefore, there's the the possibility that if you have an environment where there are a lot of collisions, cut through methodology can actually result in a lot of having to retransmit frames. And then lastly, there's fragment free, which we need to consider. Now, fragment free is a foot in each camp. Okay, it's not as slow as store and forward. It's not as fast as cut through. It's not as safe as store and forward, but it's safer than cut through. So what fragment free does is it waits until the first 64 bytes of the frame are collected. And then it starts, which is past the destination address, and then it starts to transmit them out. Now, 64 bytes is actually a magic number. Now, we don't talk about it too much, and it's not referenced at all in the CCNA version 3 exam, which I think is unfortunate now, but because the technology has pretty much evolved past it. But 64 bytes is a magical number. And the reason it's magical is that it's related to the maximum, it's related to the latest point sorry, not the latest point, it's related to the earliest point in a frame at which a collision can be detected. So the vast majority of collisions in any network, irrespective of its diameter, will occur in the first 60, so no, I was right, the latest, the first 64 bytes of the frame. So what it's basically saying, what it's basically betting on is if I get to the 64th byte and I haven't detected a collision, there's not going to be, I'm confident there's not going to be a collision, and it sends a packet out. Now, without going back too much into layer 1 and too much detail, the reason it's 64 bytes is based on the timing used in Ethernet transmission. Okay, so there might be a resource, one of the resources might talk a little bit about it, but it's quite an old concept now and not something that we need to worry about too much. But just understand that that first 64 bytes is related to the timing of Ethernet transmission. So now, spanning tree. Okay, switching loops. As mentioned by default, the switch will forward broadcast, unknown unicast, and multicast frames at all ports, except the one in which it came in on. So we know that. Loops can be created via redundant cabling and therefore may result in endlessly forwarding traffic, which then chokes the network completely. So we use spanning tree to prevent that from happening. So if we just look at this diagram here, which doesn't get too much more complex than this, it's that's about it. So we can see that there are multiple two directions in which this host can send effectively to itself here. But if we assume that there are multiple hosts hanging off these switches, you can see there is multiple directions it can transverse. Okay, it can go up through switch 2 to 1 to 3 to 5 and back again, or it can go this way as well. Without spanning tree, how does it know which way to go? And the answer is really it depends on the MAC address table of the switch. So for instance, this MAC address table here on this particular switch will have a listing obviously of exit ports and associated MAC addresses. So depending on which port a frame has come in initially when that MAC address table has been built, that will determine which port that particular frame will flow out on the way out. Of course, if you get to a position where two frames arrive at the same time with the same source MAC address, exactly the same time is pretty unlikely, but then you may get the case where the switch really doesn't know where to send it, gets confused. And in any case, when we get to the point where we've got broadcast or unknown unicast, then because there's two potential ways for it to go, you can imagine if this guy sends out a broadcast, because the switch doesn't know what to do with it, it has an all destinations MAC address, it will send it out towards switch 5 and send it out towards switch 2. Switch 2 does the same thing, it sends it out towards switch 1, switch 5 sends it out towards switch 3, and all of a sudden switch 1 gets it from two directions. And so there's that possibility of packets looping around endlessly and aimlessly. Spanning tree, or 802.11d, as it's known, that's the IEEE standard for it, 802.11d, and I suggest that you do memorize that if you don't know it already. And that's what we use in the switched environment to prevent these loops from occurring. So what this basically does is allows the switches to communicate, to communicate via a set of what are called bridge protocol data units, which we'll look at in a second, using a algorithm which allows them to form a loop-free topology irrespective of the physical cabling by blocking certain ports to achieve the most optimal free path at any one time. So the redundancy still exists. It's just that logically those ports are blocked. So there is only ever one specific path to any destination at a time. So the redundancy is maintained because if a port that is set to a forwarding state suddenly, so an uplink or redundant link suddenly becomes blocked or becomes faulty, or the cable is disconnected, or something similar, then the other port that has been blocked has the ability to be re-enabled and then start to pass off frames and traffic. So the way in which they build this view up of the spanning tree network is by using things called bridge protocol data units. So that's BDPU, it should be BPDU, so apologies for that. It is a BPDU, bridge protocol data unit. And this basically allows the bridges to communicate, or switches to communicate between each other and build up an idea of the topology of the network. Now, BPDUs are sent every 2 seconds out of every port, unless the port's in a shutdown or disabled state. The BPDUs are forwarded using the multicast MAC address, as you see there on your screen. Now, it needs to be multicast. Doesn't want to be broadcast, because then all hosts connected to the switch, regardless of what they are, all devices would have to listen to it. It can't be a unicast for obvious reasons, because there's more than one host that needs to look at it. So it's sent to multicast. So that multicast MAC address is, so the switches are automatically tuned, if you like, into listen to that multicast MAC address. Okay, where other devices, routers, end hosts are not tuned to listen to that, so they don't bother looking at it. And we'll look at this more in detail in a minute. Some types of spanning tree. So there are some others which we can also talk about, maybe on the next slide or certainly in the resource, but I'll mention them anyway. So there's common spanning tree, which is a single tree used across all VLANs on a switch. So switches, as we know, can have multiple VLANs, not just a single VLAN. In fact, in this day and age, it's very rare to find a switch with a single VLAN in any enterprise network of any size. And indeed, if you are using switches, particularly decent, high quality, expensive switches, then chances are you are going to have a great many VLANs.
So Matt, I might just jump in for a sec.
Yeah, sure.
We're getting a bit of chat, and maybe if you could go back a couple of slides, actually. We've had a few questions and a few notes about 802.1d versus 802.11d.
Yes, indeed. That's a very good question. I'm glad someone's brought that up. They are correct. It is 802.1d.
Radio. Well, we'll fix
that's
the slide.
a typo. That's a typo in that slide. Very good, people. Very, very good. Of course, that was in there deliberately just to see if you'd catch it.
Yeah, I'm sure.
No, it wasn't. It's just a typo. Very good, guys. Very good. 802.1d.
Right. Yes. There you go, folks.
Excellent work. You would have thought I'd picked that up myself after all these years, but
no, you've got a job to do. You're just presenting.
There you go. So very good. Well done.
Thanks.
Well done, guys out there. Well done, team. Okay. So common spanning tree, as I was saying, single tree across all VLANs. Per VLAN spanning tree, pretty obvious what that does, I would think, is it allows you to do a copy of the spanning tree for every VLAN on a switch. So if you have 20 VLANs on the switch, you'll have you could potentially have 20 different versions of spanning tree. You also don't have to. You can use common spanning tree, but if you're using PVST, that's what would happen. And then we have PVST Plus, which is just an enhancement that allows core spanning tree to work with PVST. So instead of having one or the other, you can have both at the same time, which can be useful. So you might have a group of VLANs that you want to use a common spanning tree for, and another group of VLANs that you want to have a spanning tree topology for each of them. So it allows you that flexibility to have both rather than just one or the other. Now, before I go any further, there is also two other versions of spanning tree which are related. There's multiple spanning tree, which is a relatively, no, it's not that recent, I guess, it's been around for a little while, but you won't see too much of that on CCNA level exams. That's more CCNP switching, and then obviously CCIE, you'll see a lot of that. So multiple spanning tree is, the best way to describe it is it's basically a mixture of the rest of them. Okay, so it's common spanning tree, PVS, it has a foot in both camps, but instead of having, like PVST plus works with common spanning tree, multiple spanning tree is basically the features of both, and plus more in the one protocol. Okay, so it's the updated version, it's the big brother if you like. PVST plus CST on steroids. There's also now, which I'm sure all of you will have heard of, a thing called rapid spanning tree, which is really not really a type of spanning tree, but more of an enhancement to spanning tree. So it allows ports and the decisions, basically the algorithm that runs to create a loop-free network, it allows that to happen much more quickly, and it allows failover to happen much more quickly. There are some other things that we'll look at shortly which also assist that, but rapid spanning tree is a separate beast on its own. So you won't need to worry about rapid spanning tree or multiple spanning tree so much at CCNA level. So the spanning tree process, to help to build the loop-free topology, there's a number of steps that got to happen. Firstly, there is the election of a root bridge. So the root bridge is, and this is where you really have to understand that bridge and switch are now used interchangeably. In terms of spanning tree, it talks about bridges, but it's really, in this day and age, we're really relating it to switches, but the term bridge is inherent in the protocol. So first of all, root bridge is elected. So that's a bridge which is the master. It controls the topology. All layer 2 traffic must head back through that. Root ports are identified. So a root port is simply the port on a switch that is closest to the root bridge. A designated port are also identified. So a designated port is a port of a segment, a network segment, that is closest to the root bridge. And where loops exist, a port will be placed in a blocking state. So the way it does that is based on a number of different things, generally the number of the port or the MAC address associated with the port, whichever one is lower will be in a forwarding state, whichever one is higher will be placed in a blocking state. And we'll see an example of that shortly. If multiple loops exist, then multiple ports will be blocked. Now, when I'm sure someone will bring up, someone will probably ask a question about fast EtherChannel or EtherChannel. So EtherChannel is basically a technology where you bundle multiple ports together and they're seen as a single logical port. In that case, for that, so there's a different level of redundancy there. You have 4 ports used for redundancy, but really, even though, yes, it is redundant because you've got 4 ports that you can generally transmit across, the real purpose of fast EtherChannel or EtherChannel, because it can be gigabit EtherChannel as well, or terabit, the main idea about that is actually to enhance throughput, not so much your redundancy. Okay, so from a spanning tree point of view, it is just considered a single logical port. Doesn't matter that there's 4 physical ports there, it's a single logical port. And there's mechanisms that are in place that's built into the back-end software of the switches.
As you were saying, someone will send a question in. Someone did ask, can VLAN be used to break broadcast domains in the network?
VLANs can, yes. Yep,
Yeah.
and we'll talk about that more next week.
Beauty.
Yes, VLANs do exactly do that, correct. All right, so root bridge election, always the first step. Best practice dictates that the root bridge should be closest to the center of the topology. So what we're talking about here is really you get to, if we just put switches in default mode and we don't do any configuration on them, they'll work it out themselves. You know, they're pretty clever. They'll go through the selection process and work it out themselves. However, best practice networking would say, don't let that happen. Configure a root bridge as the root bridge. So configure your network so you've got a root bridge that you know is the root bridge. If you just connect everything together, yes, I'll work it out, but without going around and physically looking at the configuration of each one, you won't know which one is the root bridge just by looking at them physically. Okay, you'll actually have to look at the configuration, look at the spanning tree protocol. However, if you set it up to say, all right, I want this one to be my root bridge, you're now protected to a certain degree. You've built your network, you know what you're going to get out of it. So best practice is you decide who the root bridge is, don't let the switches decide. So the root bridge election is basically determined by two things. There's a switch priority, and then there's the MAC address that is also taken into consideration, so the system MAC address of the switch in question. So by default, the priority on all switches, and we're talking Cisco switches here, okay, generally this is the same across all vendors, although some vendors like to be smart Alex and be a bit different. But in a Cisco world, the default is 32768. Just an arbitrary value, halfway between 0 and 65535. The reason it's in the middle is because it then allows you scope to increase or decrease based on what you want to see as a network designer. So in this case, the lowest priority wins. So the lowest switch priority will be elected the root bridge. So you can see if they're all set to default priority, no one wins. So it's got to go to a tie. In that case, it will go to the lowest MAC address, the lowest numerical MAC address. Okay, so again, switches are no different to any other network connected device. They all have specific MAC addresses assigned to them. So in this case, that is what breaks the tie should there be one. If we combine the priority together with the MAC address, that's called the bridge ID. So the bridge identification. And you'll see that quite a lot. So the root port is a port on each switch with the lowest cost, in other words, closest, as I said before, to the root bridge. Now each switch has one root port only. The root bridge has no root ports because it is a bridge, so all ports are equally close. But each switch will have one root port only. And this is typically based on the bandwidth of the links available. Okay, now when we're talking about the bandwidth of the ports or the bandwidth of the links, we're obviously only talking about links that are interswitch links. Okay, so it doesn't take into account anything that's connected to an end host or a router or a firewall or anything else. It's only interswitch links. So yes, this is a bit of an old table, but it gives you the historical costs as well. So a 10 meg link, for example, is a cost of 100. A 100 meg link is a cost of 19. There's an interesting story behind that, which I won't go into, but why it's 19. And gigabit links are 4. Now, obviously, as we get faster and faster and faster, there's less room for scope. So 10 gig links, terabyte links, obviously faster again. So it's the lowest cost. So in this case, if we had a 10 meg link and a 100 meg link connected between a couple of switches to give a bit of redundancy, obviously the root port is going to be the 100 meg port, not the 10 meg port, which has a cost of 100. So designated ports. A designated port is required for each network segment. So every segment of network must have a designated port. It must have the lowest cost to the root bridge, lowest path cost to the root bridge. Designated ports are never blocked. So if, for example, so what that's basically saying is every network segment must have an unblocked path to the network, which makes complete sense. A port cannot be both a designated port and a root port. Okay, so it's the lowest path cost to the root bridge, not the lowest cost to the root bridge, not the lowest. So with the root ports, we're based on bandwidth. Okay, so it's a bandwidth to the links. With a designated port, it's related to the path cost. So that's an accumulation of all the bandwidth costs between it and the root bridge. So if you think of it, the way this works, if you've got a topology where you've got 10 switches stacked together, so the designated port on the 10th switch is going to have the cost of going to the 9th, to the 8th, to the 7th, to the 6th, to the 5th, and so on back to the root port. So it's got that accumulation of port costs. So that's the difference between the designated port and the root port in terms of the cost. So the root port is just related to the actual individual bandwidth of that particular port. The designated port is related to the accumulated cost right across the switch stack. So where you get a case where a tie occurs in both the port cost and the bridge ID, the port ID will determine the overall winner. So in other words, we've got two ports that exact the same cost. Port ID will then determine the winner. So whichever the lower port ID is. So if you've got port 24 and 23 connected, port 23 will then become the designated port. So there's an example there in all its glory. So it's got pretty much everything in one, this particular diagram. So we can see root bridge. Why is it the root bridge? Because it's set to priority 100. Everything else is, oh, hang on, there we go. We have got a difference. Very good. Okay, so this guy is a root bridge. He's set to priority 100. So if we go through that election process, we go priority first, right? So priority 100, he beats this guy because he's 32768. He beats this guy because he's also 32768, and he beats switch 5, again, because he's got a lower priority. However, he's got the same priority as switch 4. So then we go to that tie MAC address, okay? This guy, switch 1, has the lowest numerical MAC address, therefore he becomes the root bridge. Fantastic. Once we know that this guy is a root bridge, then all these designated and root ports are calculated as per our discussion we've just had. So again, root bridge doesn't have any root ports, it's only got designated ports. These guys here have one root port, which is the closest to the root bridge. So in this case for switch 2, obviously the one that is directly connected to the root bridge is the closest port, so it's the root port. Similarly with switch 3. Their designated port, however, in this case, the designated port for switch 2 is the one that's connected to this network segment here, because for this particular network segment, this wire here, this port here on switch 2 has the lowest accumulated cost to the root bridge. Similarly, when we get down to switch 4, we have root port. This guy, this port here is the root port because it's closest to the destination, to the root bridge. It could go this way, yes, but it's got 1, 2, 3 hops this way, 1, 2 hops that way. Now, bear in mind, remember that we're talking about bandwidth, not hops, but in simple speak, we don't have bandwidth on this particular graphic. So if we assume that everything's just 100 meg, then we're going to, well, actually it's written on 100 meg, isn't it? So we've got 100 meg there. So that's 100 meg, 200 meg. So port cost of 19. I'm getting confused here. Sorry, guys. 100 meg links have a port cost of 19. So this guy's got a port cost 19, 38. Going this way, he's got 19,
sorry,
38,
Matt.
57.
Sorry, we're not seeing the directional points.
Oh, okay. Do you want me to? Okay. Hang on.
Yeah. Sorry about that.
No, that's all right. Okay, is that better? Can you see that?
Yep.
Okay, so I'll just say that again. You can see that the bandwidth are all 100 meg. So therefore, this guy here, this switch here, to get to the root bridge, it can go one or two ways. It can travel up this way through switch 2, or it can travel this way through switch 5 and switch 3. So if we look at if we understand that 100 meg link is a cost of 19 for the purpose of coming to a root port calculation, then if we go up through switch 2, we have a port cost of 19 and another 19, which gives us a total cost of 38. If we go this way, we have port cost of 19, an additional 19 giving us 38, additional 19 giving us 57. So transiting this way is going to be a higher cost than going this way, and therefore this port connected to switch 2 becomes the root port, and this port here does not become the root port, but it does become the designated port for this segment here. Okay, so designated, very, very important to have that clear distinction between a root port and a designated port. So the root port is the closest port to the root bridge for that switch, whereas a designated port is the closest port to the root bridge for that segment or that wire, because it's quite possible that you could have other hosts connected in here if there was other switches involved. In this case, it's relatively simple because we've just got connections between switches not involving other hosts. And then the last point I want to bring your attention to is this guy down here. He's blocked. Yeah, he's in an X state. He's blocked because he's the redundant path. He's been determined that it's quicker to go this way. It's quicker for this switch to go that way. We know that it can go this way, but it's slower to go that way, so we're going to block that port. Now, it doesn't matter which switch blocks that port, but it will always be blocked on one end. Okay, let's just turn that highlighty off. Yep. Next. Okay, so our port states. Yep, what have I done there?
While we're looking for that, got an interesting question from Michael. What happens when the root bridge goes down?
When the root bridge goes, that is a very good question. When the root bridge goes down, what will basically happen is the other switches involved, so all the other switches will go through that election process again. And again, they just go through the same election process again, so that the root bridge will be completely re-elected based on whatever. So if we look at this case here, so if we said root bridge went down, then they would go through the election process again, and switch 4 would be elected as a root bridge because it has the lowest priority. If it was to also go down, then the other 3 switches would have a tie because they're all the same priority. Therefore, switch 2, because it's got the lowest MAC address, would then become the root bridge, and so on and so forth. So if once one goes down, the election process just goes through again. Good question. Okay, so in terms of the port states, the states in which ports can exist, there is a blocking state, and this is the default, where the port does not forward any frames at all, and it doesn't listen to MAC addresses, but it will accept BPDUs. So it still is involved with the spanning tree process. However, it doesn't listen for MAC addresses, so it doesn't build a MAC address table, and it doesn't forward any frames. So it's just sitting there, just listening very politely. In listening mode, so just on the blocking too, anytime you plug a device, a switch or a router or a laptop or whatever the case may be, any sort of host into a switch, the first thing a switch does is puts it in blocking mode, and it'll just sit there doing nothing. Listening is where a port will progress, is the next state that it'll progress to. And it will only listen if the switch believes that the port will not be shut down in order to eliminate a loop. So in other words, if it's not connected to another switch, if it detects that it's not connected to a different switch, and there is technology that allows that to happen, which is outside the scope of our discussion just now, but if it detects that it's not connected to a switch and it's connected to an end host, then it will start to listen. If it thinks that it might be shut down because there's a loop, then it will just sort of sit there for a little longer. A port in a listening state will accept BPDUs, so it still participates in spanning tree if it has to. And it will participate in the election process as well. So a port that's listening can still go through that process of building up the election, but it won't learn any MAC addresses. Next state is learning. So after a delay called a forward delay, a port will listen. So the port in a listening state can be then elected as a root port or a designated port, and then once that's happened, it'll be placed into a learning state, in which case it'll still listen to BPDUs, but it will also start to learn MAC addresses, but it's still not forwarding at this stage. Then after another forward delay, and we'll look at these times in a minute, the port will then transit into the forwarding state, and it can now do anything. Can send, receive frames. All designated ports, root ports, and non-uplink ports will eventually become forwarding ports. Okay, if it's not a designated port, it will be placed into a blocking mode, in which case it's just sitting there listening to BPDUs. And there is one more, which is it's disabled. So this is where you can set it down. you can administratively set it, or if you have port security enabled and it's violated, then it will disable the port. And in that case, it doesn't participate even in STP. So it's the only state that doesn't participate in listening to BPDUs. Now, the timers. Couple of timers. So there's a hello timer, which is 2 seconds by default. And all that does is determine how often the BPDUs are sent out. That's all it does. That can be changed. I advise you not to change that. Not at all. That can result in all sorts of nasty things happening. The forward delay we were just talking about is 15 seconds. So the forward delay timer is responsible for determining how long a switch waits before it goes from listening to learning and then learning to forwarding. Okay, so 30 seconds. So from the time when you plug a switch in, when you plug a port into a switch, it will start, if it's not detecting it's connected to another switch, it will start listening straight away. After 15 seconds, it will go into learning mode. After another 15 seconds, it'll go into full-on forwarding mode. So 30 seconds. That's in standard spanning tree. Rapid spanning tree, it's different, but again, that's a discussion for a different day. So this delay is simply built in to ensure that spanning tree protocol has plenty of time to detect any loops that may be there. And then last of all, there's a max age timer, which is 20 seconds by default. So this is a timer that says how long a switch has to keep the BPDU info from a neighboring switch before it discards it. So in other words, switches send BPDUs every 2 seconds, yes? If for 10 intervals in a row, 20 seconds, I don't get a BPDU from my neighbor, I will then assume that it's gone down and I will chuck out all the information that I know from that neighbor. And away it goes. Okay, so that's the maximum age. Hence, when we talk about spanning tree transition time, we always say it takes between 30 and 50 seconds before a link will become active in regular spanning tree. The reason it's 30 to 50 is because of this max age timer. So if it's related to pulling a link out of a switch or a redundant link out, then it's got to wait 20 seconds before, or if something goes wrong and it doesn't get BPDUs for 20 seconds, it's got to wait that 20 seconds before it ages that information out and then starts going through the process again. And then the next 30 seconds is where it'll go from learning, start to calculate the spanning tree, go through the election process, then listening, keep going again, finalize the process, and now we're getting into forwarding stage. So it can be 30 to 50 seconds. You only, if you're going to change, and as I said before, I would advise that you don't change the timers, but if you ever do, only change them on the root bridge, because they will then be propagated downstream to all the other switches. But there's no real need for you to get outside the defaults, particularly nowadays where we've got rapid spanning tree, which is quicker again. So what constitutes a topology change? So it's important, obviously, that if the topology of your network changes, that the switches detect that and then rebuild the network topology accordingly. So a topology change will occur if an interface transitions into a forwarding state. So in other words, it's gone through the whole election process, it understands where it fits in the overall scheme of things, and I'm going to start forwarding information. Or alternatively, an interface is already forwarding or learning, and then it goes into a blocking state. So in other words, either come on or you go off. The switch that is directly impacted by that change will send what's called a topology change notification BPDU. So it sends that information directly to the root bridge by whatever path it has to take to get back to the root bridge. And all it does is it says that a change occurs, but not what the change was. So it doesn't say whether a link's come up or gone down. Once the root bridge receives that topology change BPDU, it will send out another BPDU with a topology change bit set to all the switches in the spanning tree. So everyone becomes aware that a change has occurred and an election may be required. Okay, there's some spanning tree enhancements, which we sort of alluded to earlier, and some of this is a little bit redundant. Well, not really, it's still important, but a little bit redundant by rapid spanning tree, but nevertheless still important concepts. So port fast was a concept that was brought in, a technology that was brought in to allow ports to immediately transition from blocking to forwarding while the spanning tree algorithm was running in the background. Okay, now this should never be enabled on interswitch links, redundant links, because it'll create massive problems. It's only to be enabled on host connected links. So hosts could be laptops or computers, routers, firewalls, load balancers, pretty much anything that's not a switch. So anything that's not involved in switching, you can enable port fast on that particular port. And what that basically means is that it will start forwarding straight away. So we know that if we plug our laptop into a network and we boot it up, often it is up and running nowadays and is trying to get an DHCP IP address before the port has got into a full transitioning state if we're using normal spanning tree. So if that's the case, it might get to the stage where, oh, I can't get an IP address, I'll give myself one, or I'll just give up trying. And then you get connection issues. So port fast is a technology that enables that port to go into a forwarding state straight away, so you avoid all those other host-related timing issues. The thing about port fast is once you enable it, topology change notifications won't be sent out. Why? Because those ports, if you've got a laptop and it's going on and off all the time, or a computer's going on and off or whatever, then that port can be bouncing quite regularly. You don't want topology change notifications sent out all the time. Okay, uplink fast is used where multiple interswitch links exist. So we've got multiple redundant paths. So yes, we've always got multiple paths in redundancy, but we might have 3, 4, 5 links. And this allows a redundant link to be placed into forwarding mode immediately a failure occurs on the primary link. So you can't configure this on a root bridge, mainly because it's the boss. But on all the other switches, if you have multiple links, you can enable uplink fast on those links, so that if the primary link goes down, the backup link will come up straight away. Bang. So it's port fast for switches. Okay, so port fast for switches basically. And then there's backbone fast, which is similar to uplink fast, but it's used for indirectly connected interfaces. So in other words, switches that are downstream. If we enable backbone fast, what this basically does is allows any switches with backbone fast configured on them to bypass that max age timer. So if they detect that, if a topology change notification comes around and they detect that there's an indirect failure, so in other words, a failure on a port that's not connected to that switch, then it will allow that backup link to come up straight away. Okay, so again, it's uplink fast is port fast for switches. Backbone fast is port fast for switches that are further downstream. So very similar technologies and related. Okay, protective mechanisms, we have root guard, which you need to know about. So that basically, all that does is stops unauthorized switches from advertising themselves as the root bridge. So it stops people from coming along and just poking a switch in and allowing them to become a root bridge. So this is enabled by port. Okay, so you enable root guard on your ports. That means no one can come up and just plug a switch in and have it overtake the spanning tree topology. And then BPDU guard, this is used on port fast enable interfaces. So as I said before, we don't want BPDUs to go out port fast enable or to be generated from port fast enabled interfaces. If they do find a BPDU coming in through a port fast enabled interface, that interface will be placed into error disable mode and will stop operating. So again, that's another way of stopping people from bringing in other switches and just plugging them into one of your port fast enabled interfaces and have that switch start sending spurious information around the network. Okay, so from a CCNA level, you need to understand, you need to know those two and understand what their purpose is. So BPDU guard on port fast enabled interfaces to stop the transition of rogue BPDUs, root guard to stop transitioning of the spanning tree to a rogue switch. And then lastly, BPDU filtering basically stops support from sending out any BPDUs at all. So it doesn't do anything, irrespective of the actual, whether it's in port fast or not. So a little bit on VLANs just quickly. So a VLAN is, again, a layer 2 construct, but it's used to create broadcast domains. So it's almost a 2.5 layer, 2.5 layer construct. So even though it's related to layer 2, and technically it's discussed as layer 2, VLANs are obviously also related to layer 3, in that they, because they split up broadcast domains, VLANs require some sort of routing functionality to transition between. And we'll talk about that more next week. Yeah, so it must have a routed device to communicate. Broadcast from one VLAN will not propagate to another, even with a layer 3 device. So this is what we've been talking about. Routers, which are layer 3 devices, or firewalls or whatever, they will not broadcast, they will not propagate broadcasts across that under any circumstances. I'll just add that, I'll just answer that question because it popped up in front of me. Seems to be a separate collision nodes to layer 2. I assume separate MAC address tables per VLAN? No. MAC address tables are related to switches and switch ports, so they're not really related to VLANs at all. So they're not separate MAC tables per VLAN, but really good question. So as an example, we have a switch here and we have 2 VLANs. Computer A and B are in VLAN 1, computer C and D are in VLAN 2. Now VLANs are completely intertwined with subnets and IP addresses. They are separate constructs, but they are always intertwined and always spoken about in the same breath. So you can see VLAN 1 is on a different subnet to VLAN 2. Okay, 172.16.1.1 and 172.17. Well, 172.16.xx, 172.17xx. So it's just an example of how you've got 2 VLANs on the same switch with 2 hosts per VLAN. Now, someone, I hope, will ask the question, can those computers talk to each other? And the answer is yes and no. So yes, the computers, computer A and B can talk to each other because they're on VLAN 1. Computer C and D can talk to each other because they're on VLAN 2. But C and D cannot talk to A and B because they're on separate VLANs and there's no routed device in that example. So that's the difference between VLANs and just switch ports, which are associated with the MAC addresses. So why do we use VLANs? A few reasons that you need to know about for CCNA, and there are some others, but these are the ones you need to know. Broadcast control. So in a pure layer 2, broadcasts are received by every host. When we implement VLANs, broadcasts won't propagate outside their own respective VLAN. For security, it enables us to logically separate users, departments, businesses by whatever construct we want to use. And flexibility and scalability. So it removes physical boundaries. Devices users can be added anywhere the VLAN exists. So for instance, you can have 10 buildings, each with a single switch in them. Those switches are connected by fiber. You can create VLAN 1 on every switch if you want to, VLAN 2 on every switch, VLAN 3 on every switch, and it doesn't matter whether your hosts are in building 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. If they're a member of VLAN 3, they will be able to talk to each other. If they're a member of VLAN 2, those ones will be able to talk to each other, so on and so forth. You even can have situations where you'll have a VLAN per building. Okay, so each building's got its own VLAN. None of those hosts will be able to, none of the hosts in any building will be able to talk to the host in any other building without the presence of a router, but so it separates them into 10 separate broadcast domains if you want to think of it that way. So VLAN membership in terms of switch ports can be assigned in 2 ways. Firstly, you can do it statically on a port-by-port basis. You can do it by group support, but you can do it by port-by-port basis if you want. Dynamically by MAC addresses using a thing called a VLAN policy membership server. What was called that now, it's now got some other funky name, but you basically using a policy server. You can do that. Or statically is much more common though, to actually go around and physically determine which ports you want in each VLAN. As I said, you can do it by MAC address by tapping into a policy server, MAC address, this MAC address on this laptop or host is in this VLAN. And as soon as it connects, it will get placed into that particular VLAN. That's not the norm. Static is much more common and much easier to manage. Particularly where you have situations where you might have hot desks or people coming in with different MAC addresses all the time, or BYOD devices or devices that regularly change over. Policy server can be a real pain in the backside, so using it statically is much more normal. VLAN port types, so two basic types you need to know about. There's the access port and the trunk port. So an access port just belongs to a single VLAN, typically connects to hosts and end users, end devices only. A trunk port will allow VLANs to span across many multiple switches, do not belong to any single VLAN, and they're fast or gigabit Ethernet ports only. So not that that's relevant for today really anyway. You're not going to run into two 10 meg ports only. So example of some ports. So we've got multiple access uplinks between trunks, so VLAN A, B, and C. If we use a trunk port, however, so in this case, we've got 3 physical links, one for each VLAN. In this case, looks much better. We've got a single link with all 3 VLANs running over a single trunk port. So it allows us to use less physical ports while having the same amount of traffic running across it. So when using trunk links, however, we need to be able to, as we've seen from this here, we need to be able to identify which frame belongs to which VLAN. And we do that by frame tagging. Basically, the frame tag is really just inserting the VLAN ID onto each frame as it goes through. So this frame is VLAN 1, this frame is VLAN 2, this frame is VLAN 3. And this only ever occurs at trunk ports because that's the only place in which multiple VLANs can pass across. And I have seen a question out of the corner of my eye about phones. There was something that popped up about phones. When you connect a phone to a switch port, particularly in the Cisco environment, it assumes that that port then becomes a trunk port. So it's exactly the same as an interswitch link, because the phone that has 2 ports in it, one to plug into your device, one to plug in for the phone itself. Typically, the way you would do it. Then that 2-port is basically seen, that 2-port device in the phone is basically seen as a switch. So it becomes across as a trunk port. So if we look at this quick example, got a couple of switches with a VLAN trunk, VLANs A and B, and we can see spread between the 2 switches, we have various devices on VLAN A and VLAN B. Okay, so that trunk port allows that to happen. So the more switches you can see, you could imagine that as you had more switches to the example and more trunk links, this would become bigger and bigger and bigger. And you could have multiple endpoints, multiple hosts in different VLANs all over your network. It doesn't matter because you've got the trunk links there to take that traffic across, that VLAN traffic across. So tagging protocols, there is only one main protocol now, it's .1Q, okay? Interswitch link ISL, Cisco only, proprietary, not very common, you'll probably never see it. You might in some rare circumstances, which is why I mention it, but you won't see that very often at all, if you ever do, depending on where the context that you work in. But .1Q is certainly the main standard, and you'll see that that's supported by all switch vendors. So .1Q is the standard, and basically all it does is it inserts the 4-byte VLAN ID into the layer 2 frame. That's all it does. It's just a tagging protocol. Trunking protocol, so .1Q tagging can be manually configured, so you can set it up manually on the switch ports, or you can use a thing called dynamic trunking protocol, which is used in the Cisco world, and there's various names for it in other switch vendors, but it's basically the same. And that automatically tags frames as they go in and out of the switch, depending on what VLAN they're configured for. The native VLAN is an important concept to understand. Basically, the idea is the frames from the native VLAN, whichever one you decide it is, and it's VLAN 1 by default, are not tagged when they're sent out the trunk port. So they're the only VLAN, the native VLAN is the only VLAN that's not tagged. This must be identically configured right across your network. So you've got to have this, you must have the same native VLAN right across it. You don't have to, according to the protocol, but in terms of if you want things to work properly, best practices suggest that you have the same native VLAN right across your network. It is set to default by 1. Best security practices would dictate that you change it to something else. Because basically what it allows to do is if you connect something in VLAN 1, it will just transmit it frames across the network without being tagged, okay, which can be a security issue. VLAN trunking protocol is a different protocol again. Sounds similar to dynamic trunking, different again, and it can be confusing. But VTP is basically used to manage your VLAN database in large environments. So where you have lots of VLANs, 10, 15, 20 VLANs, VTP is a protocol that allows the consolidation of those VLANs across all your switches that are members of the VTP domain. Okay, so a collection of switches together in a domain basically shares VLAN information so that everyone's got the same idea of the VLANs right across the network. So you're not having to manage statically VLANs on every single switch, or you don't have the situation where you've got different switches with different numbers, different VLAN numbers. Everything's exactly the same. So VTP advertisements or updates are sent out every 300 seconds. Their updates are sent by VLAN 1 by default. Okay, another good reason for not having that is a native VLAN. And VTP versions 1, 2, and 3 have various, so VTP 3 is the latest version, various improvements, mainly rotating around security and speed of delivery. Best practices usually suggest that you do your VLAN statically rather than use VTP, because there is always the opportunity that someone can come along with a different switch, different version of VTP database and wipe everything out if you're using VTP. So in most cases, you're not going to use it, but it's there if you want to. In terms of VTP modes that a switch can exist in, there is server, client, and transparent. Basically, the difference is if your VTP switch, if your switch is a VTP server, that's where you need to create, modify, and delete your VLAN entries, and it sends out those updates every 300 seconds to all the other switches that are connected to it. A client VTP, a switch in VTP client mode, can take that information from the servers and update its own VLAN table, but you can't modify, it can't modify the table. So you can't add and delete VLANs on a client. You can only listen and update their own tables using VTP. Then we have transparent mode, which they don't care about VTP. They don't even listen to VTP. They'll forward VTP packets, they don't care. So any VLANs that exist on that switch are local only to that switch. They're not related to any other switch in the network. Best practices now basically suggest that you just use switches in transparent mode and you manually go and configure your VLANs on each of the switches. The concept of VTP pruning, which is disabled by default, is basically that it won't allow VLANs to VLAN traffic across a switch link if that VLAN doesn't exist on the destination switch. So say for example here we have switch 1 which has got VLANs A, B and C, switch 2 has VLANs A and B, and switch 3 has VLAN C. In this case, if there was traffic for VLAN A and B, then switch 1 would not let it transit across this link because there's no need for it to go across that link because there's nothing on VLAN A and B on that switch. Similarly, going this way, it wouldn't propagate any traffic for VLAN C. And that's all it basically does, okay? Just stops that. So that's why it's called pruning. It just basically prunes the VTP tree. All right, so that's it for layer 2. I'm sure we've got questions.
Oh, we've got plenty, but we've also got Jason waiting in the wings. So I've tagged 3 or 4 questions as ones we'll answer live that you should be able to see. Matt, if you could maybe answer those ones, and the rest we'll just have to rely on forums and chat function.
Okay, I've got lots.
Yes, but there should be 3 or 4 that are just saying that we'd like to answer these questions live.
Oh, yep, here we go, okay.
If you could read the questions and then chuck them answer.
Yep, okay, so first one is, how can computers on different VLANs communicate? Do I need to introduce a gateway? Yes, a gateway of some sort, or a layer 3 device. So some device that can do routing, and I think I saw someone else talk about it. We talk about that a lot next week. So you need some sort of routing device to communicate between VLANs, that's correct. Could you use VLANs to enforce security, put Wi-Fi points on one VLAN to protect the business Ethernet? Yes, you can. There is a concept also called, it's just gone out of my head, but basically VLANs, private VLANs, that will only talk to specific ports that are enabled for that particular VLAN. So you can use VLANs to enforce security to a degree. It's obviously not the ultimate. There are methods to jump across that, but it is one way that you can do it. And last one, why use a trunk instead of a router? Well, a router does a different thing. So a router is about routing traffic between VLANs, whereas a trunk link is about sending traffic or sending layer 2 information between switches. So you still need a router to talk between the VLANs, but the trunk is about sending multiple traffic from multiple VLANs across the same switch ports. That doesn't mean that those VLANs can talk between each other. It just allows that traffic from multiple VLANs to pass across those switch links. So they work at a slightly different level. You still need a router to talk between the VLANs, however. And that's it.
Great, thanks so much, Matt. We'll no doubt say good night later on. I might just introduce you all now, folks, to Jason. Jason graduated from CSU in 2003, and since then he's been lecturing in the School of Computing and Mathematics, which he is now Dean of, or Associate Dean, I should say. Jason's taught subjects across a broad range of IT areas, including computing programming, cryptography, information security, and software architecture, and he's been working closely with IT Masters in that time. So could you all please welcome Jason?
Thanks, Guy. Thanks very much for the introduction. Can you hear me okay?
Yep.
That's always a good start. Good evening, everyone. Great to be with you here tonight. Actually, Guy just gave me a bit of a promotion. I'm not actually the Dean. I'm the Associate Head of School, Computing and Maths with Charles Sturt University. I've also been a course director. No doubt I know some of you out there who might be doing this program. So
next step, Jason, no doubt.
No doubt. So thanks for that, Guy, and I'll use you as a referee.
Feel free.
So what I want to talk to you about tonight, for those of you who may want to go further with your study, we offer a full range of IT postgraduate courses here at Charles Sturt. And for those interested, let's talk a bit about some of those tonight. I want to focus on two of them, our Master of Cloud Computing, and we also have a Master of Networking and Systems Administration. We have a number of other master's programs. I'm not going to discuss all of them tonight. We have programs in mobile application development, IT management, cybersecurity, project management, you name them. We probably have an IT postgraduate degree in that area. So let's just focus on a couple of them, as well as sort of the pros and cons of studying a master's degree at university, why you might want to enroll with Charles Sturt, how long it would take, how much it would cost, etc. So once again, if you type any questions in, also happy to get emails from anyone, jhowarth@csu.edu.au. So there's a few pictures of CSU. We're a regionally based institution within Australia. We're a very large university, but we do have campuses spread over a lot of different areas. So we have campuses in Bathurst, Wagga, Albury, Port Macquarie, also partner campuses in Sydney and Melbourne and overseas. So there's a few pictures from some of our regional campuses. I think predominantly though, what Charles Sturt University is an online university. So we have around about 24,000 students studying degrees with us online. So we are one of the, if not the major online university within Australia, but by no means small either in terms of on campus. We have about 16,000 students studying with us at each of our various campus locations overall, not at each one. So in terms of why you would want to get a master's, or why you would want to get a master's from Charles Sturt University, a few salient points. we're obviously a fully fledged Australian university. Our master's degrees are fully accredited under the Australian Qualifications Framework. So they're genuine master's degrees recognised throughout Australia and the world. They're designed, and certainly all the programs I'm going to talk about tonight, are designed to be studied online and part-time. So we're very much as well in an institution that's focused on those in the profession. So highly practical master's programs. Masters as well are a great way for you to stand out from the crowd in terms of your qualifications. A little while back, if we look at the Australian census, that is the one before the last one that kind of didn't work, the Australian census data showed that there was around about 2.3 million Australians with a bachelor's degree. And when you move into the postgraduate space, the master's space, that drops to around about 500,000 or 600,000. So as you climb up the academic ladder, the competition becomes thinner. So certainly in terms of getting ahead in your professions, a master's degree is a great way to stand out from the crowd. Charles Sturt University as well is not just a leading university, but the leading university in Australia for IT postgraduate enrolments. We're number one. And it's, university is not a popularity contest, but when the market, elects you as number one in terms of enrolments, it's a sign that we're doing something right. And I'm just going to drag across now. You can check out for yourself. There's a great little guide in Australia called the Good Universities Guide. And I'll just pull that across there. You can Google that yourselves. One area where Charles Sturt continually excels is actually with our full-time employment rating. So this is the Good Universities Guide from 2017-18. There's lots of different ratings. Full-time employment, in Australia, Charles Sturt University is at the top of the pack. So 83.9%. And you can see there that the criteria is the proportion of graduates who were employed full-time 4 months after completing their course. So we're at the top of the hill in terms of Australian universities. That reflects on the fact that not only are we great at getting people jobs, but also that we attract people from the professions themselves. I'll let you look further into the Good Universities Guide, but it's another reason why you might consider Charles Sturt. Another reason, many people feel that they're kind of locked out of tertiary education, maybe, and it's not an uncommon scenario that people got into the IT industry, perhaps out of school, following a different pathway, and they never actually got around to getting an undergraduate degree. And one thing you should bear in mind that if you have had some time in the industry, and by time we mean sort of minimum 3 years in a reasonably senior position. It's something we need to talk with you about as part of the application process. But there is an entry pathway for you into a master's program based on your industry experience. So if you feel that, you haven't got a bachelor's, but you have had a fair bit of experience within the industry, please talk to us, because there is a pathway potentially for you into a master's program without having to do any additional units or costing you extra money. So that's an important consideration. We mentioned the market leader online. The stats kind of speak for themselves there. Obviously, these change from year to year, but we're a major player in the online environment, and that has been the case since our inception virtually in 1989. Of course, we were more paper-based back then. We've moved now into the online sphere, but we still are the major player in that distance education space, as well as the market leader, as I said before, in the IT space in terms of enrolments. And we've been there now for nearly a decade in terms of every other institution in Australia having the most postgraduate IT students in our programs. So let's talk about a couple of the programs tonight. There's two of them that I want to focus on. Obviously, the short course that you're doing with Matt on the CCNA, it actually is derived from one of our subjects here at Charles Sturt. And it's a bit of a taster, if you like, for what some of our subject content might look like, how it's delivered in terms of web-based lectures. So if you do like the content and the material that you're being delivered, it is very much indicative of the kind of material that we have in our programs at CSU. And you can see on the screen then, if I kind of highlight it below or pointed it, ITE 526 Practical Internetworking is the actual subject. I'll just go back. The actual subject from which the CCNA 3 course is derived, that is currently being taught by Matt. So the Master of Cloud Computing and Virtualization is a course all about the design and management of cloud architectures, managing and working with clouds, cloud security, also containing sort of subjects on software-defined networking and virtualization. And as with all of our master's degrees, it consists of 12 subjects. So you can see on the screen there, we have a left and a right-hand side in terms of the subject blocks. As part of this course, you need to do 7 what are called core subjects. They're on the left. So core subjects are those which everyone must do, unless for some reason you might get credit or recognition of prior learning. So everyone must do those core subjects, not negotiable. They're kind of what we define as the absolute core of what you need to learn if you're going to be a master of cloud and virtualization. On the right-hand side, you can see there's a number of electives. That gives you a bit of a scope to tailor the award to suit yourself. So there's 5 subjects there. You need to choose sort of 2 from one block, 3 from another, and that makes up your entire master award, 12 subjects. That will take you about 2 years to complete part-time. So that's going at a fairly steady rate. You can speed things up, you can slow things down. If we go through very quickly and just look at some of these units, many of them in terms of their content are reasonably intuitive from the names. So as part of the core, we have a subject there on cloud computing, where you're looking at various cloud-based systems and architectures. You're looking at cloud delivery models, planning for migration to the cloud infrastructure, and so on. Cloud privacy and security is fairly self-explanatory in terms of what you're looking at. Another interesting subject in the core there, ITC 571, Emerging Technologies and Innovation, is what we call a capstone subject. So that subject occurs at the end of your course, and it really is the opportunity for you to choose a project, an area that you want to study or work on, and to be able to design and execute a project in the area that you're focused on. In this particular course, that'll be cloud and virtualization. You might be analyzing cloud architectures or designing a new architecture. If you're studying security, you might be analyzing cryptographic protocols as part of that subject. If you're studying programming, you might be building a mobile app. So the idea of that subject is that it kind of brings together everything you learn within the course and allows you to branch out on your own and produce something new. Another key feature of our programs is that they're kind of balanced between the theoretical and the hands-on. So there are subjects here where you're looking at networking protocols, information security principles, the fundamentals of object-oriented programming. So all of the kind of the principles and the theoreticals, but there's also a lot of subjects that are highly practical. And as an indication of that, a lot of units that link with content from specific industry certifications. So there are subjects that are based around content from the CCNA, for example, subjects that are based around content from the Amazon Web Services certifications. So for example, ITE 531, Architecting Cloud Solutions, is all about designing an optimal cloud-based solution in accordance with a set of project requirements, but it's very much using and preparing you for the Amazon Web Services Certified Solutions certification. So some of these subjects are highly practical in the sense that they are based on industry certification content. Now, rather than me sort of talking through each of the units, you can Google these course names. Say, for example, the Master of Cloud Computing and Virtualization. What you'll get is an online course brochure, which looks something like this. There's the name of the course, Master of Cloud. You can scroll down and there's a little section there. We can just close it. Why study this course? A little section there called subjects. Okay, you can expand that and you'll find that each of the subject links is actually clickable. So for example, we could take a subject, let's say hacking countermeasures, ITE 516, just click on that and you'll see that there'll be a description of the subject. So in this particular unit, you're learning about perimeter defenses, scanning and attacking networks, hopefully for the purpose of good. And the linkage there between this subject and the EC Council Certified Ethical Hacker Certification. Scroll a bit further down and you'll see the actual syllabus, the topics that you'll cover as part of this unit. So penetration testing, Trojans, denial of service, SQL injections, and so on. So you can do that, that Google search yourself and actually look at those courses and the subjects contained in them at your leisure. So that's the Master of Cloud. The other one that we can look at briefly tonight is the Master of Networking and Systems Administration, all about sort of teaching you around the design, implementation and management of computer networks. As with the previous course, it has a set of core subjects, 6 in total, some of them shared in common with the previous program. So we have subjects there on internetworking with TCP/IP. That's very much a theoretical subject where you're looking at the fundamentals and foundations of the TCP/IP protocol. Hacking countermeasures is part of that core. We looked at that one based on the EC Council Certified Ethical Hacker certification. We have a subject there, a core subject on virtualization, which is based around VMware, the VMware technologies, and in fact, once again, prepares you to take the examination to become a VMware certified professional. It doesn't go the whole way, still some work for you to do. Ultimately, you need to sit that certification outside the course, but it does get you started, and it does show the strong practical emphasis of the program. Also some soft skills, what we call soft skills subject there as well. Professional communications, obviously that's, you know, incredibly important for any IT professional. That subject takes you through informal communication using email to more formal writing, right up to, you know, presenting in front of a crowd. So they're incredibly important skills to learn. Another unit there in the core, topics in IT ethics, is looking, of course, at IT ethics, but also at other important issues such as privacy, intellectual property, internet content regulation, and so on. So a really good mix of units. And once again, we have the elective units there on the right-hand side where you get to choose to suit your interest. Okay, so I mentioned before that our programs are online. There's no need for you to set foot on a campus if you don't want to. Of course, we do love to see people for graduation, but the whole thing can be done entirely online within certain constraints. But you know, you can also go to a certain extent at your own pace. You can speed things up, you can slow things down, you can take leaves of absence. When you do enroll in our courses and you do enroll in specific subjects, you're given access to a learning management system called Blackboard. And for every subject you enroll in, you'll see a learning management system site which looks something like this, where you get access to all your materials, your subject outline, which outlines your assessments when they're due, various other information about the subject, a discussion board for communicating with other students. You can see on the left here as well, online meeting room. Most of our units have live online lectures, regular online lectures, using webinar software as part of our delivery. They're also recorded for those of you who can't make it on the night. Going further down, there are within the learning management systems sections on various topics. So in addition to your textbook and any other study that you might do, we have dedicated online resources for each topic that you study within the units. There's also here an electronic assignment submission and tracking system. So of course, these days when you have to submit assignments, it's not a matter of posting them in. We don't email them either. We upload them to this EAST's assignment tracking system. So everything is transacted online, which makes it really convenient for you as the learner. Now, some of you may, not necessarily know about where a master's fits into the overall Australian qualification hierarchy. Just to give you the big picture there, in terms of tertiary awards, at the bottom, still very important, are your undergraduate awards. They're your bachelor's degrees. Then we move up into graduate certificates and graduate diplomas, which are typically sort of master's level content, but a smaller amount. So a graduate certificate is typically 4 subjects, a graduate diploma, 8 subjects. Then you're moving up to sort of the top of your hierarchy, a master's degree, which is what we're talking about here. And for those who want to go even further, there are your doctorates, where you get to be, called doctor and to submit a massive research thesis for those of you who want to go down that path. But in terms of coursework programs, master's is pretty much at the top of the academic hierarchy. Okay, so what are the entry requirements for these programs? If you have a bachelor's degree or higher, plus some industry experience, so we aren't looking at, completely people typically outside the IT sphere. So, I mean, these are degrees that are intended for people who are strongly IT focused already. So that they're not so-called conversion degrees. So if you have a bachelor's degree or higher and you have some experience within the industry, it might not be in the particular topic area that you're studying, but you'll get straight into the master's. There's no kind of quota there. If you have industry experience, I mentioned before, but no bachelor's degree, say you've been working as a systems administrator for 5 years, or you have a lot of experience developing programs or other IT experience, typically you can come into the master's through what we call a graduate certificate pathway. A graduate certificate pathway is a subset of the master's. It's 4 subjects, master's being 12. So if you have that experience, I'll show in a moment how that works. You enter through the graduate certificate pathway onto the master's. You don't actually do any additional subjects. So there's no disadvantage in coming in via that pathway. For those of you who do want to find out whether or not you're eligible, maybe you don't want to go to the trouble of applying and finding out you're not eligible, you can actually check your eligibility by going to the IT Masters website, www.itmasters.edu.au, or you can apply online and your eligibility will be assessed as part of that application process. I mentioned before about entering through a grad certificate pathway. The way that works is that all of the graduate certificates that we offer are subsets of a master's. So if you're coming in on the basis of work experience, we would put you in a graduate certificate. You would do 4 subjects. If you get through that okay, then you simply transfer into the master's. Those 4 subjects are credited, leaving 8 subjects to get your master's. So there's absolutely no disadvantage whatsoever in coming in via that route. In fact, in some ways, you get an extra award, so it's good. And, you can elect to do that as well. You don't sort of have to go straight into the master's, even if you're eligible. You can come in via that grad cert pathway, which is often a good way to kind of test out the course. So in terms of time commitment, I've got to say that from next year, we're going to be offering 6 intake sessions for the year. So you'll be able to start in January, February, May, July, August, or November. So 6 different intake sessions from next year. That's kind of a trial. We'll see how that goes, but hopefully that will continue. But there's also an intake session coming up fairly soon, which starts in November. So as a rule of thumb, you're going to study about 6 subjects per year as a standard part-time load. So it's 2 years to get your master's. You can speed things up, you can slow things down. That's an average. In terms of the study commitment, obviously it varies depending on experience, but we factor about 10 hours study per week per subject. So if you're doing 2 subjects in a session, you're looking at around about 20 hours of commitment per week. You can vary the study load, as I said, and you get busy at work, you need to take some leave, you're allowed a certain number of leave periods, no questions asked, where you can just take time off studying, still be enrolled in the course, come back later and resume where you left off. So it is very flexible these days. A great way to reduce the cost and time is actually to get credit. And credit is certainly available for our master's programs. We give credit on the basis of previous relevant postgraduate study. So maybe you've done a course in networking fundamentals with some other institution at the postgraduate level. We would certainly look at that for credit. You might have industry certifications. Maybe you've got the CCNA. Maybe you'll get it after this short course. Maybe you've got the CCNP. Maybe you've got ethical hacking certifications. We would look at industry certifications as well for credit into our programs. So there are two pathways there to get credit. We don't give credit for work experience. You know, work experience helps you get into the program, but there's no credit for that. And we don't give credit on the basis of sort of undergraduate awards. They're at a different educational level. We do assess credit as well as part of the application process. But if you're really keen to learn more before you apply about how much credit you might get, once again, you can complete the eligibility form, which is available at the IT Masters website there on screen. In terms of cost, always a big factor. The cost per subject, and I guess there's two figures here because there's a 2017 cost, and there's certainly still an intake into 2017, and there's a 2018 cost. These fees are grandfathered, if you like. So if you do start in 2017, that $31.50 per subject will be held constant through the degree. I mean, there might be small CPI increases, but the base figure is constant. So $31.50 per subject. If you're starting in 2017, you can multiply that by 12 to work out the total cost. In 2018, for Australian and New Zealand students, $32.50. If you're coming to us internationally, studying by distance, $32.50 and $33.50 in 2018. Now it's not a trivial cost, obviously, but you know, you also need to bear in mind the return on investment for these awards. Also keep in mind that any textbooks that you need as part of the course are supplied. So typically all the resources that you need in terms of, you know, books and software is typically supplied unless otherwise stated within your subject. There's a small student services and amenities fee per session as well. It's around about $34. I don't have the exact cost. For those of you who, I mean, certainly you should, if this is part of your development for your career, you should certainly talk to your accountant as perhaps being able to claim the cost of your education back on tax. Some people as well apply for a loan through the Commonwealth Government fee help program, so they don't have to pay the fees up front. That's paid back through the taxation system more gradually. So there are different options there for you in terms of fees. In terms of applying, you can do that directly by going to csu.edu.au/apply. We have a session which is coming up over the Christmas period. It kicks off on the 13th of November. So for those of you really keen, if you want to get involved by starting in that session, the advice would be to apply, you know, fairly soon. We also have 2018 intakes starting on each of the dates there listed. Some of these intakes haven't yet opened for applications, but they will be doing so very shortly. Most of them, the February, July and November intakes have opened. We are experimenting, as I said, with a January intake early next year, and that intake will be open very, very soon for those of you really keen to get started straight after Christmas. So plenty of opportunities there for you to enter the program and make a start. It certainly costs nothing to apply. There's no risk involved with that. And indeed, you're not up for any money either until you've been enrolled in the subject for around about 3 or 4 weeks. So if in doubt, costs nothing to apply, enroll in a subject, study it for a couple of weeks before what we call the census date, which kicks in around about 3 weeks into the session, and you can pull out without any financial penalty. So there is a sort of a try before you buy option. If you do want more info about any of the information I've spoken about tonight, you can phone me. There's my number on screen. Email me. Always very happy to hear from prospective students. My colleague as well at IT Masters, Neil McCosh, great guy, great bloke to have a chat with. You can call him there on the number on screen, or email Neil, and he'll be also very happy to answer any questions you have, particularly around credit and eligibility. Okay, so thanks very much. Appreciate your time tonight. I'm going to stop sharing, and I don't know if there's any Q&A you want me to address.
There is just a couple questions. I know we'll direct most of the serious questions to Neil about credit. But there's a question from Sim asking whether there's a time frame for certifications, industry certifications being included for credits.
Yes, Sim, there is. I mean, typically we would be looking at certifications up to around about 5 years old. So if you've got something obviously 10 years old, that's probably not going to cut it in terms of credit. But the rule of thumb is generally up to 5 years currency for your industry certification in terms of credit.
Great. And a question from Tommy, I guess loosely, what assistance do you provide for international students in terms of, I guess, charting the applications for residency and those sorts of things?
In terms, I mean, we don't, to be honest, we don't get a lot of international students. I mean, this is not an on-campus program, so we do have internationals who study with us in their home country by distance education. So in terms of residency, that's not typically something we get involved in with these particular courses. Our main audiences would be domestic Australian students or students studying overseas by distance education. So residency, I've got to say, is not a huge part of our business model for these particular programs.
Fair enough. All right. Well, thank you very much for that, Jason. Thanks for everyone else for hanging around as well. Matt, do you have any signing off comments?
Yeah, just a couple of quick ones. Just if you see the slideshow up there. So next week we're going to be talking about routing technologies. So stuff, the routing concepts, DV versus LS, so it's distant vector versus link state protocols, interior versus exterior. Have a look at OSPF and RIP version 2. So some of the questions, I was actually in the process of answering some questions. I got kicked, and unfortunately when I come back I couldn't see them again, so I apologise to anyone I left hanging. But next week, some of those questions you asked about routing and VLANs and spanning tree and how it all relates, we'll start to look at those a bit more. So, but other than that, yeah, thank you for your attendance.
Beauty. Thanks so much to you, Matt, to you, Jason, and to Diane and Holly and James hanging around, listening out there, being the support staff for IT Masters, and thank you all for continuing to participate. We'll see you all next week.
Thanks, everyone. See you next week. Thanks, team. Great job again.